So we left the last video on a cliffhanger here. Otter was wondering, why do these solutions form in the first place? And we said that one of the possible reasons that a solution could form is entropy. Which then begs the question, what is entropy? What is this thing we're talking about? Well, we're going to dive into entropy a lot more in a lot more detail in a later chapter. For now, we are going to think of entropy as the tendency for disorder or randomness. Maybe a slightly better way of thinking of it is entropy is the tendency for things to move towards being as spread out as possible. That's a slightly better definition, slightly more accurate definition. Because truthfully, entropy is not actually the tendency for things to move towards disorder. It just so happens that when things spread out as much as possible, when they occupy as many states as possible, they end up being random and disordered. So for our purposes, either one of those definitions will work. Again, just because we're keeping it fairly simple, just know that if you go into a physics level, like a PhD level physics class, and you tell someone entropy is the tendency for things to become more random, though they might get upset with you because it's not technically true, but it works for our purposes to think of it that way. So just as an example here, if you have a solution on one side of a container that is separated from a pure solvent, like water, on the other side of the container. If you remove the barrier, so you don't have to mix it, you don't have to stick your hand in there and mix it all up. If you just remove the barrier, if you allow it to mix, it will eventually reach the point where there is a uniform concentration throughout. The solute that was just on one side will gradually spread out and occupy the whole container evenly. Same thing over here. If you start off with one gas on one side of a container and another gas on the other side of the container, if you remove the barrier so that they're no longer kept away from each other, they will both spread out and occupy the container equally. So again, the slightly better definition is that things spread out as much as possible. But again, here at the same time, you can see how it does become more random. Because before there was some order here. We had one molecule on this side and one molecule on this side, and now they're all mixed together. So it is technically more random in that sense. So, if entropy is saying that everything always wants to go to be more disordered, everything wants to spread out as much as possible and be more random, why does the whole universe not look like this, where it's just a big mess, where everything's just kind of mashed together, just kind of blah, just everything everywhere mixed and messy? Why isn't the whole universe like that? And the answer is that entropy is not the only thing that determines if things will come together, that determines if solutions are going to form. There is a second force that is at play here, and that is enthalpy. Enthalpy is something you should have discussed in General Chemistry 1. In General Chemistry 1, we mostly discussed it in terms of whether a reaction was going to be endothermic or exothermic, and measuring the chemical potential that results in the potential change that happens in a chemical reaction. So we're going to be expanding on that a little bit. It is still just enthalpy, but we're now broadening how we're viewing enthalpy beyond just a chemical reaction occurring, because intermolecular forces are also going to be not necessarily determined by, but it's kind of the other way around, actually. So the types of intermolecular forces that are present, the types of intermolecular forces that are possible, will determine if enthalpy is going to favor or disfavor a process from occurring. So to take a slightly closer look at that, when we have a solution form, there are three different intermolecular interactions that take place. There are solute-solute interactions, which are to say intermolecular forces between two different solute molecules. The stronger those interactions are, the less likely a solution is to form. Because if the two solute molecules really like each other, then why would they want to go associate with those solvent molecules? They're with their buddies. They don't want to separate. Another type of interaction that takes place in solutions is solvent-solvent interactions. So this is the same thing as the previous one, just now this is the interaction between two different solvent molecules. It's very much the same as the first in that the stronger the solvent-solvent interactions, the less likely it is for a solution to be formed. Because if the solvent molecules really like each other, if they have very strong intermolecular forces between each other, then why would they want to go and associate with those solute molecules? They're with their buddies. They're happy where they are. The third type of interaction that can take place is the interaction between solvent and solute. So this is the one interaction that if it is very strong, it could cause the solution to form. So this is the attraction between the solvent and solute, and the greater this interaction, the more likely it is to overcome these first two. So essentially, these first two are saying, they're saying no to solutions form, to having solutions form. And this one is saying, yes, we want solutions to form. So if these two are stronger, essentially, than this one, there's a good chance that the solution will not form. It's not guaranteed, but there's a good chance that we won't get a solution, because essentially the solutes say, we like each other, and the solvents say, we like each other, and they look at each other and say, and we don't like those other ones over there. We don't like those molecules. We have no intermolecular or strong intermolecular forces with the other molecules, so we're just going to stick with our buddies here. So it's really these three interactions that the relative strength of these three interactions determine if enthalpy will favor or disfavor a solution from forming. And again, just to remind you real quick, these are the types of intermolecular forces that we have going on here. We can have dispersion, we can have dipole-dipole, we can have hydrogen bonding, and we can have ion dipole. So any of those four can be participating in these three different types of interactions. So the general rule here, which I kind of hinted at just a second ago, is that if the interaction between the solvent and solute is stronger than the interaction between the solvents and the interaction between the solutes, then the solution is going to form. And really with no exceptions there, because entropy is always, for our purposes anyway, we are going to say that entropy is always going to be in favor of solutions mixing. In reality, there are actually a few exceptions to that, but they're very rare exceptions, and so we're just going to pretend like they don't exist. Just ignore that. Yeah, just ignore those. Not there. So for our purposes, we're going to say entropy is always going to favor a solution forming. So if enthalpy is favoring the solution forming, which is what we see here, because this is stronger, the force that wants them to mix is stronger than the force that wants them to stay separate, then the solution is going to form. If they're about the same, so the new interactions, so to speak, when the solution forms between the solvent and the solute molecules is about the same as it was before. So the solvent-solvent interaction is roughly the same as the solvent-solute interaction is roughly the same as the solvent-solvent and solute-solute. Sorry, it's hard to say that quickly. If they're about the same, then the solution is still going to form, because even though enthalpy is essentially saying, I don't really care one way or the other, it's about the same for me, entropy is still there saying, solution, solution, solution. Entropy is always wanting the things to mix. And so because the entropy wants it to mix, and enthalpy doesn't really care one way or the other, then it's going to mix. It's only in this last scenario here, where the solvent-solute interaction is weaker than the solvent-solvent and solute-solute interactions, where it's not likely, we'll say, that the solution is going to form. It could still form. You have to take it on a case-by-case basis. And as we'll see in a later chapter, on a temperature-by-temperature basis as well, because it will change with temperature, which is something we're not really going to focus on too much in this chapter. All right. We're going to talk a little bit more about this topic here in the next video, but I don't want to make this a half-hour long video. So we're going to go ahead and stop here for now and take a slightly more detailed look at this and how it relates to whether mixing processes are endothermic or exothermic in the next video.